This is the solution to Chapter 22, Problem 23 of the 9th edition. We have two charged rings along an axis, charge Q1 and charge Q2. The charges are unknown. In between the charges, at a certain point along the axis, is point P. The distance between the centers of the two rings is d. Both rings have a radius r. The distance from Q1 to point P is r, and the distance from the center of Q2 to point P is 2r. So, we're told that the net electric field at P is 0, and we are asked to find the ratio of Q1 to Q2. Before doing any math, we can see that, first of all, the electric field at P is going to be completely along the axis. Since both rings are centered around the axis, then the radial components cancel, so all we have is an x-axis component. As well, we know that the net field is the sum of the two x components from charge 1 and charge 2. So, because the charges are on opposite sides of P, then those field components are going in opposite directions if the charges have the same sign. So we know that the charges must have the same sign so that the field components will cancel. Again, if both charges are positive or both charges are negative. So the sign of Q1 over Q2 is positive. As well, we know that since Q2 is farther away from P, then the charge itself must be bigger to match the field of Q1. So the magnitude of Q1 over Q2 is less than 1. So putting those together, we know that the ratio of Q1 to Q2 has to be greater than 0 and less than 1 before doing any math. One solution that works is the solution, the trivial solution, where Q1 equals Q2. In other words, there are no charges, and so not only is the net field at P 0, the net field everywhere would be 0. So to do our calculations, since each ring is symmetric about the x-axis, then that means all the points on each ring are the same distance from point P, and at the same angle. So, we can treat each ring as a point charge at a distance r from the x-axis. So here we have the first ring. We have point P, charge Q1, we have the radius of the ring is r, and the distance from P to the center of the ring is r. That means that by the Pythagorean theorem, the distance from P to Q1 is the square root of r squared plus r squared. And we can call this angle theta 1. So, the net field, the magnitude of the net field at P due to charge 1 is 1 over 4 pi epsilon naught times Q1 over r squared plus r squared. And the x component of the field at P due to charge 1 is just the magnitude times the cos of theta 1. The cos of theta 1 is r over the square root of 2r squared, which is just 1 over the root of 2 because it's obviously an angle of 45 degrees. Similarly, if we look at the second ring, now we have a charge Q2. Again, the radius is r. The distance from P to the center of the ring is 2r. And so, by the Pythagorean theorem, the distance from P to Q2 is the square root of 2r all squared plus r squared. And the angle, we can call it theta 2. So, again, the magnitude of the electric field at P due to charge 2 is given by this. And again, the x component of the field at P due to charge 2 is just the magnitude times the cos of theta 2, which is this. So, given that the x component due to charge 1 and the x component due to charge 2 cancel each other, not worrying about the signs, we will have that this is true. So when we substitute in the equations for the magnitudes, we get this, which reduces to this. So we wind up with the ratio of q1 to q2 is 4 square root of 2 over 5 square root of 5, which is approximately 0.51. In order to check our answer, remember that we already said from our first analysis that q1 over q2 had to be greater than 0 and less than 1. So our value of 0.51 meets that requirement, so therefore our solution is reasonable.